Hi guys, welcome to this lesson on exercise where I hope to help you put together a few things in terms of the effects of these hormones on metabolism. It's not a particularly easy subject to integrate in terms of the effects of all these hormones, but exercise tends to bring some of them together. And so, and it also tends to explain a few things that may be still puzzling you about these responses. And it's a good one to cover because we've already covered it in depth in terms of the cardiovascular responses in vital fluids. Okay, so exercise is, of course, an increased demand of energy, and that's what we're going to be talking about here. The response to an increased demand for energy. So how do you measure exercise? Not a particularly easy question to answer. If you look in the literature, there are a variety of different ways that it's done. One thing you can do is just measure the rate at which oxygen is consumed. The higher the rate of oxygen consumption, the higher the metabolism and the more you're demanding energy. Okay. You can also measure it by as a percentage of the maximum oxygen uptake by your body. So you take up the amount of oxygen that you need, and it's taken up into your blood at the same rate that it's used. Otherwise, you would blow up like a balloon. Okay, and so if you know what the VO2 max is, you can measure exercise intensity as a percentage of that. This would be the maximal rate at which oxygen can be consumed by a given individual at a maximum exercise. Okay. You can actually measure the rate of doing work. That would typically be done in watts, which is the rate of energy conversion. Okay, and we aren't going to do that. We aren't going to talk about it. Heart rate, as you know, tends to go up with exercise, and you can measure heart rate as a measure of intensity of work. Okay. So having said all that, let's look at this mysterious MET. So 1 MET is equal to 3.5 mils of oxygen per kilogram per minute of oxygen consumption. It's a metabolic equivalent of task, okay? It's basically an arbitrary unit, okay? And it's an arbitrary unit which is basically 1 when you're watching TV, okay? If you're watching TV, you are exercising with an intensity of 1 MET, okay? Not much of an exercise, if you ask me. When you're sleeping, it's 0.9, so watching TV, not much above that. Okay? If you're riding, your METs go up because your intensity has gone up. If we go from light intensity to moderate intensity activities, our METCs go up from there. Bicycling on a stationary bike gives you 3. Bicycling outside, presumably at less than 10 miles an hour, gives you 4. On a stationary bike, when you're really going at it, it gives you 5.5. And then you have vigorous exercise where you're jogging at 7 or you're rope jumping at 10. Okay, so your METs go up as your intensity of exercise goes up. All right. So catecholamines are central to the response to exercise. I think you guys know that. We talked a lot in vital fluids about the fact that sympathetic tone goes up when you exercise, and what that does in terms of sustaining blood pressure. You get vasoconstriction to tissues that are not active, and you get an increase in heart rate and an increase in cardiac output, and that maintains blood pressure as you get vasodilation in your active tissues and your active muscle due to the buildup of metabolic substrates. Okay, so with mild exercise, you get a little bit of an increase in catecholamines. With moderate, you get a bigger increase. With heavier exercise, you get an even bigger increase in epinephrine, and here we have norepinephrine on this side. Okay, all right. So the increase in catecholamines has effects on glucagon and insulin. Higher catecholamines tend to increase glucagon secretion, and that should make some sense to you because you're utilizing substrate at a higher rate, and glucagon will tend to keep that substrate level high in the plasma. Okay, it'll tend to keep it maintained. So you'll want more glucagon to maintain that glucose level in the face of an increased consumption. On the other hand, insulin secretion goes down because you don't want more insulin when your plasma glucose is decreasing and when you've increased the rate of utilization. You want less insulin because insulin will tend to remove glucose from the blood and send it into storage. And that's not what you want here. You're exercising, you're using glucose, you want less insulin, less glucose uptake so you can maintain those plasma levels high, okay? All right, so mobilization of lipid and carbohydrate, sources of substrate in response to an increased glucagon and a decreased insulin, okay? So that makes some sense to you. Now, on the level of the muscle, let's look at how the muscle takes that glucose up and uses it. So our normal insulin-dependent response is demonstrated on the right-hand side here, okay? So we have insulin binding to the insulin receptor, which is tyrosine kinase. It has its targets. Amongst the things that it does is it activates PI3K, PI3 kinase. That leads to an increase in glucose transporters in the sarcolemmal membrane, and you get an increase in glucose uptake when you have high insulin, okay? That's the way it normally works. Here's the problem. This works when you're resting. When you're exercising, you're getting more catecholamines. And as I just showed you, that means that you're suppressing insulin release and increasing glucagon release, okay? So, what's the deal? Okay, if I'm suppressing insulin, then I'm suppressing glucose uptake. If I'm suppressing glucose uptake, how does my active tissue get more glucose? Well, there are a couple of different things to remember here. First of all, you're using more glucose, okay? So that's sustaining a gradient for glucose across this membrane. So despite the decrease in transporters here, if you maintain your glucose level in your plasma, you're going to get a certain amount of an increase in transport just because you're using the glucose more, okay? But the other thing to note is that in muscle, there is an insulin-independent mechanism by which you can increase glucose transporters in the membrane. So with exercise, you're stimulating the muscle to contract, you guys know that, okay? And that stimulation is causing the release of calcium from the sarcoplasmic reticulum. It does this in skeletal muscle in the same way that it does in cardiac muscle, okay? So this increase in calcium in muscle will cause, through a hormone-independent mechanism, glucose transporters to be incorporated into the membrane. So because you've got more calcium release in your muscle, that calcium is causing more incorporation of glucose into the membrane. And this is insulin independent, which means insulin can go down, and this still happens. And because you're exercising and your calcium is going up, this is going up at the same time that this side is going down. So what that does is it increases glucose uptake, despite the fact that your insulin is down and your insulin-dependent mechanisms are decreasing glucose insertion into the membrane. This maintains that glucose transport, the glucose transporters. It increases the insertion of glucose transporters into the membrane, and that sustains glucose uptake. So this is an insulin-dependent local mechanism. So as long as you're sustaining plasma glucose, you're sustaining uptake into the tissue that needs it because of this increased calcium. So this is a typical example of how you can sustain glucose uptake in the face of reduced insulin levels that you get. So the question has been, how can you change glucose uptake with, for instance, cortisol or something like that? How can you suppress glucose uptake, or with catecholamines for that matter, and still get an increase in glucose transport in active tissue like active muscle here? And the answer is because of local mechanisms like this one, where an increase in calcium increases the glucose transporters in the membrane in an insulin-independent manner so that you can still get an increase in glucose transport. So your systemic hormonal response is to maintain plasma glucose. Your local response is to make sure that that glucose has a way to get into the cell and sustain the increase in metabolism. All right? There we go. Insulin-independent increase in glucose uptake. And again, glycogenolysis and lipolysis also increase in a calcium-dependent, hormone-independent manner. So in addition to sustained glucose uptake, you're getting more hydrolysis of glycogen to increase cytosolic glucose, and you're getting more lipolysis to, again, maintain glucose levels and increase fatty acids, which can be utilized for substrate as well, okay? So generally speaking, our hormones increase glycogenolysis, they increase generally speaking, our glycogenolysis and our lipolysis are also increased in this hormone-independent way in order to maintain energetic substrate in the face of an increased demand, okay? All right, so let's look at the duration of exercise here and the contribution of each of these to the percentage of oxygen uptake. That means how much is each of these contributing to maintaining metabolism in the face of exercise with increasing amounts of time. So if we look at short-term exercise, 40 minutes or less, our primary source of, we utilize both fatty acids and muscle glycogen to a large extent. With the short-term, glycogenolysis is the most important for a short-term burst of exercise. It's contributing a lot to maintaining metabolism at this relatively short 40-minute mark, okay? I'm going to show you a graph in a minute where that will be even more graphically demonstrated. On the other hand, at longer bouts of exercise, you tend to use more fat-free fatty acids. So you'll notice your utilization of fatty acids is going up here with longer bursts of exercise. So at the 240-minute mark, you're using more fatty acids than you were at the 40-minute mark. On the other hand, the use of glycogen has gone down, and that's basically because you're running out of it. So you're using a lot of glycogen in the short term at 40 minutes, and that's decreased quite a bit at 240 minutes because there isn't much glycogen left. And the use of glucose increases and then decreases back down basically to the level that you started with. So it's kind of maintained more or less the same throughout, despite the increase in duration. Okay. So here's another way of demonstrating how you utilize substrate with an increased bout of exercise. So if you exercise the first few minutes, your primary source of energy is going to be the ATP that you've already got, plus creatine phosphate, which can be utilized by creatine phosphokinase to produce ATP. This is a readily utilizable substrate. It doesn't last very long. You run out of it very quickly, but it can be quickly converted to ATP in a fairly short manner. So the first couple of minutes, the first minute or two, you can sustain exercise mostly through the use of this creatine phosphate and the ATP that you already have. If you go a few minutes more, now anaerobic metabolism takes place, and now you're using more glycolysis. And you're starting to use up muscle glycogen, okay? Glycogen in the muscle is being broken down into glucose, which is then being metabolized, okay? If you go longer than that, you transition into more aerobic oxidation now, and your mitochondria are getting involved. You're still drawing from the muscle glycogen, which is producing glucose, which is being used by aerobic oxidation. You're drawing from liver glycogen, which is dumping glucose into the bloodstream, and that is also being utilized via aerobic oxidation, okay? And then finally, as I mentioned on the previous slide, with longer term exercise, You continue to use aerobic oxidation, but now your primary source is becoming plasma fatty acids. You're liberating those fatty acids from adipose tissue, and that's becoming a primary source for your aerobic metabolism and for sustaining metabolism in the face of a longer bout of exercise, okay? So short term, you're utilizing muscle glycogen. Long term, you're utilizing fatty acids, okay? So if we look at how this process of exercise develops, the first thing that you see when you start to exercise is an increase in sympathetic tone. I think you guys know that. And that is going to cause an increase in catecholamines, which are going to have all the cardiovascular effects that you would expect: increased heart rate, increased cardiac output, vasoconstriction in non-active areas. In muscle, you're getting an increase in glycogenolysis and lipolysis, okay? So in order to generate more substrate for utilization in your active muscle, okay? In response to the increase in catecholamines. We also get, through peripheral nervous system afferents, signaling to the hypothalamus. And what the hypothalamus is going to do is it's going to increase CRH, GHRH, and TRH. And you can see that here. So now we have, as the exercise goes on, we have stimulation of the response of the hypothalamus, and it's going to start secreting these. Let's start with CRH. In response to that, you get an increase in ACTH from the pituitary. So the CRH comes from the hypothalamus down the portal system to the anterior pituitary, which releases ACTH. That goes to the adrenal medulla and causes the release of cortisol into the bloodstream, which increases proteolysis and gluconeogenesis to supply more substrate to your active skeletal muscle, okay? At the same time, you are increasing GHRH, which will increase growth hormone. THRH increases TSH, which will increase thyroid hormone. And you can see that here. Here's our ACTH and our cortisol, and now we add to that. We have an increase in growth hormone and an increase in thyroid hormone. Okay, and these are going to contribute their effects during exercise. You're going to increase metabolism, make it more efficient, and you're going to utilize growth hormone, for instance, to sustain plasma glucose, okay? All right, and in addition, we have ADP and ANP, atrionatriuretic peptide, and these are going to regulate blood volume, and you sweat out all your fluid during sustained exercise, okay? So they're part of this integrated response to exercise as well, okay? And you guys know all about that. Okay, so here we have a chart with all of our hormones in column number 1. And the first thing that you'll notice in this chart is that as we go to increasing exercise intensity, all of our relevant hormones, ACTH, cortisol, catecholamine, glucagon, growth hormone, insulin, we've talked about these. These all, except insulin, they all go up with increasing intensity of exercise, okay? Insulin is down, of course, with exercise. But growth hormone, glucagon, cortisol, these go up as exercise intensity increases. So that's the first thing that you should notice in this chart, okay? The second thing, and this is sort of interesting, your anticipatory response. Remember, this is the response of your system before you actually start to exercise. Remember from vital fluids, you get a certain amount of vasodilation during this response. Well, 3 hormones have been isolated as being at least partially responsible for this. You get an increase in cortisol, an increase in catecholamine, and an increase in ACTH, which goes with cortisol. So these seem to be involved in the anticipatory response. Again, it's kind of a mysterious response, but they go up during anticipation, so they seem to be involved in that response. So that's of some interest in this chart. The other thing that's really interesting is that aerobic training, really low intensity exercise, actually decreases these hormones, or doesn't, which is kind of weird. They increase, all but insulin increase with exercise intensity, but at light exercise, these hormones actually go down, which is kind of interesting. Nobody knows why, as far as I know, but they do, okay? All right, so here is here a graph of our epinephrine release over time as we exercise. And the first thing you'll notice is that over time, as you exercise, you get more and more epinephrine release. More and more catecholamines accumulate and are released as the time of exercise goes up. So see that here, here, and here, okay? So your epinephrine release goes up with an increased time of exercise. At the same time, you'll also notice that epinephrine release goes up with intensity. So if I pick a time, 20 minutes, and I look at fairly light exercise, where it's only 40 to 50% of VO2 max, and I compare that to heavier intensity exercise, like 82 to 90%, 80 to 90% of VO2 max, you'll notice that my epinephrine release has gone up quite a bit more with the higher intensity exercise. So in addition to going up with time, our epinephrine release also goes up with intensity. And you can see that as a change in slope here, so that at any given time you have more epinephrine release with a higher intensity, okay? And finally, this is a graph that sort of demonstrates cortisol with an increase in exercise intensity. And you'll notice first, at low intensity, cortisol is actually down below normal. It actually goes down with low intensity aerobic exercise. Don't know why, it just does, okay? On the other hand, it does what you'd expect with increasing intensity, and at higher intensity exercise, you get higher levels of plasma cortisol, and of course that helps you sustain your plasma glucose, okay? All right, that's exercise in a nutshell. Thank you for your attention.